All right, so today we'll be moving on to the first lesson of our final unit, which is on two-variable statistics. The first lesson today we'll be looking at scatter plots and linear correlation. Okay, so scatter plots and linear correlation are used to determine how one variable is affected by another variable. So you have your dependent variable and you have your independent variable. Independent, as always, goes on the x-axis, and the dependent variable goes on the y-axis. So, for example, does time studied affect test results? So our two variables here, one is time, right? How much time you spent studying, and the second is the results on the test. Okay, so in this case, the independent variable would be the amount of time spent studying, and the dependent variable is the test results, as we are saying that the test results are dependent on the amount of time that one had spent studying. Okay, what types of correlation can we have? Linear correlation. So one variable tends to be proportional to changes in the other. So, for example, as x goes up by 1, y also goes up by 1 every time, right? Perfect, direct, positive linear correlation. Y increases at a constant rate as x increases. Okay, so if you have a straight line, that tells us we have a linear correlation, and if it's going up and to the right, that tells us positive, and what that's saying is, as x is increasing, so is y. Okay, and then on the flip side, if we have a perfect or inverse negative linear correlation, our line here goes down and to the right. And what that's telling us is as x increases, y decreases. Okay, so positive going up and to the right, and negative going down and to the right. Okay, so moving on from there. What are scatter plots? Basically, they show relationships graphically. Another term that we would have seen probably going back to grade 9 again, line of best fit. The stronger the correlation, the more closely the data points cluster around the line of best fit. Okay, and we'll look at that in a little bit more detail down below. Another, I guess, piece of terminology here, correlation coefficient. So this is a number that is between -1 and 1, and what it does is it gives us a quantitative measure of the strength of a linear correlation. So what that means is it actually gives us a number, that's why it says quantitative, to tell us how strong of a linear correlation we have between two variables. Okay, based on how strong the relation is, that will indicate how closely the data points cluster around the line of best fit. And here we see Pearson product moment coefficient of correlation, PMCC, or Pearson's R. So basically from all of that, we need to use our formula here, where R, lowercase r here, will represent the correlation coefficient. And here is the formula as to how you would figure out that R value. Okay. At first glance, this formula looks like it's very complicated. It's actually not if you just look at it or take it step by step. Remember, this thing that looks like, I guess, a capital E somewhat, or sigma as it's called, means sum of. So this is the sum of all your x's multiplied by y. Subtract the sum of all your x's times the sum of all your y's. Here, take all of your x values, square them, and then add them, right? So the sum of all your x squareds minus, and now notice the difference here, the sum of x is in brackets and the squared is on the outside. So what this means is you take all of your x values, add them together, and then whatever you get as the sum, you square that afterwards. Okay, so that's that part. Over here we have the same thing, except we're using y now. So take all your y values separately and square them, and then add all the squares to get the sum of your y squareds. Here we take our y values, add them all together, and then whatever the sum is, we square that. Okay, and the only one here that I didn't mention is the n. And these three ends are all representative of the same thing, which is the number of data points that you have. Okay, so again, it looks very complicated. It takes some time, but if you do it step by step, it actually isn't all that bad to go ahead and calculate. Okay. In terms of what does the number mean? So this will give us a number between -1 and +1. And again, like we said, that number tells us how strong, if we go back up here, sorry, it gives a quantitative measure of the strength of a linear correlation. So basically how strong or how weak is the correlation between your two variables. Okay, so here's a key to tell you how to interpret the correlation coefficient. The closer you are to 1 or -1, the stronger your relationship is. If it's +1, it's a positive correlation, and if you're closer to or exactly at -1, then you have a perfectly strong, weak, or negative, sorry, not strong or weak, a perfectly negative correlation. Okay, and as you get closer to 0, your correlations get weaker. Okay, so kind of divide it up into thirds. If you're between 0 and 1/3 or 0 and -1/3, classify that as weak. If we're between 1/3 and 2/3, we classify that as moderate. And if we're between 2/3 and 1 on either side, the negative side or the positive side, then we classify that as strong. Okay. In terms of examples, what would these look like graphically? So the stronger your relation, the more your data points cluster around the line of best fit. So here we can see our data points are all clustered around the line of best fit. So that's representing a strong relationship, and it's a strong positive because our graph is going up and to the right. This middle one here, we can see our data points are clustered around the graph, or the line of best fit, I should say, but not nearly as strongly as these are. They're more spread out. So this would be considered a moderate relationship, and it is negative because our line of best fit is going down and to the right. And then a weak relationship would basically have our points basically all over the place, not clustered around any sort of line of best fit. So this one here, we would say weak or no correlation. Okay, so that's what they would look like graphically. So going on to an example, a farmer wants to determine whether there is a relationship between the mean temperature during the growing season and the size of his wheat crop. He assembles the following data for the last 6 crops. Okay, so in the first column here, we have our temperatures, or the mean temperature, and in the second column, we have our yield in terms of tons per hectare. So in this case, our x value, the independent variable, would be the temperature, and then the yield would be the dependent variable, right? So we're seeing basically how the yield is impacted by the temperature. Okay, so does a scatter plot of these data indicate any linear correlation between the two variables? So if we go ahead, plot our temperatures on the x-axis, plot our yields on the y-axis, we can see a general trend, right? You can see they're kind of going up and to the right, but they're not that close together, the data points. So we would say it's a moderate positive correlation, okay? Moderate because the data points are forming, you can see a trend going up and to the right, but they're not super close together, so that's why they're moderate. And because they're generally going up and to the right, that's why it's a positive correlation. Okay, so we could say that graphically, moderate positive correlation. The other way we could identify what type of correlation we have is to actually compute the correlation coefficient and get an exact number value to tell us what kind of relation we have, whether it's weak, moderate, strong, and whether it's positive or negative. Okay, so the first 2 columns here are the numbers that were given to us, the temperatures in the first column, the yield in the second column. And based on our formula to solve for R, or the correlation coefficient, we can see it down here. Basically, we need to get the sum of all of x times y, the sum of x, the sum of y, the sum of the x squareds, and again, the sum of x, the sum of the y squareds, and the sum of y. So all of those numbers that we need are here in the table we see above. So adding all of our x values, we get 48. Adding all of our y values, we get 12.9. Then squaring our x's, so 4 squared is 16, 8 squared is 64, 10 squared is 100, so on and so forth. Adding up all of the x squared, so the sum of all the x squareds is 418. Then do the same thing with all of these y values, right? You can see these y values are all squared over here. And then to get the sum of our y squareds, it's 28.33. And then the last thing we said we needed was the product of x and y and the sum of all the products. So the product, meaning 4 times 1.6, gives us 6.4. 8 times 2.4 gives us 19.2. We go ahead, add those all together. So the sum of x times y, or sum of all of the x's times their corresponding y, is 105.3. Okay, so once we have all of these numbers down here at the bottom, we're basically just plugging those numbers in to the formula. Okay, and the one we didn't, I guess, calculate up above is n, and that's how many data points do we have. We can just count them: 1, 2, 3, 4, 5, and 6. Okay, so plugging in our numbers, so let me go up here again. N is 6, and I'm just going to move this down just a touch so we can see the numerator here. N is 6. The sum of x times y, 105.3, plug that in there. Then over here is the sum of the x's, which is 48, multiplied by the sum of the y's, which is 12.9, which we can see right there. And then for the denominator, we have n down here, which is 6. Then we have the sum of all of the x squareds, which is 418, and that goes there. Then the sum of all the x's squared, right? So the sum of all the x's is 48, and that's squared. And then moving on to the second square brackets, we have n again, which is 6. The sum of all the y squareds, which we calculated to be 28.33. And then subtract the sum of all the y's, which is 12.9 squared. Okay, so all of these numbers up here are basically what we plugged into our formula there to get us to this step. At this point, you just let your calculator basically do all the work, and simplifying that, you get a coefficient value of 0.467. And again, it's positive 0.467, so it's a positive correlation. And because it's between 1/3 and 2/3, or you can say it's between 0.33 and 0.67, it's considered a moderate correlation. Okay, so the graph showed us that, but in case we were unsure, by looking at the graph, just to get a bit more of a concrete number and interpretation, we get this correlation coefficient, and that definitely tells us that we have a moderate positive correlation. Okay. Finally, what can the farmer conclude about the relationship between the mean temperatures during the growing season and and the wheat yields on his farm? So because it's a moderate positive correlation, still moderate, we can say the temperature does have some effect on the number of crops, but because it is only moderate, there could be other factors that impact the yield, right? So things like sunlight, the rain, bugs, anything like that, that could have impact on helping the yield or decreasing the yield. Okay, so again, because it's moderate, we can say, yeah, there is definitely somewhat of an impact the temperature has on the number of crops, but because it's only moderate, there's other factors at play. Okay, so that's it for today's lesson. Any questions, as always, feel free to email, and yeah, we'll leave it at that then. Okay.